smaller data sets than today, that those models started expressing very interesting properties that I, as a psychologist, would expect to see in humans, such as mood-like states or ability to recognize and appropriately react to emotions. And that kind of inspired my interest. So I decided to switch my research from trying to use computational methods to understand humans to just try to understand computational methods. And of course, this is not a new problem. We have a department of statistics here at Stanford where folks, for decades have been studying statistical tools. And even simple statistical tools have emergent properties that are very difficult to understand for us humans. Take linear regression. If you actually look more closely, there are some interesting phenomena there that just defy human intuition. And of course, when you train now networks with millions of neurons and many layers, those models are much more there in the kind of a black box, interesting for psychologists space. And I'm not sure if this is Elana, it's a good time for me to just start the talk.
Yep, let's do it. Let's start. Thank you.
Great. So I'll talk about emergent properties in large language models, and I will skip a little bit just to make sure I should finish at 1:30, right? So we can have time for questions. Let me try to finish earlier, and we can just top up with content as needed. So emergent properties, that's my title, emergent properties in LLMs. Now, folks, you're all familiar with emergent properties. Take life, for example. Now, life is an emergent property of underlying chemicals. And now the interesting aspect of emergent properties is that you can know everything about the underlying simple elements. Like you can be an excellent chemist and understand chemistry very, very well. And yet this will not let you understand or predict the properties of what happens when simple chemicals and other elements come together to create life. Another example is our brain. You could have a perfect understanding of how a single neuron works, and yet this will give you no idea about how consciousness, emotions, goal-oriented behavior, poetry, or other outputs of the entire brain work. And I'm particularly interested in the emergent properties of large language models. As you folks know, those models are trained in fairly on the surface trivial way. We take a neural net composed of several 100,000 to several million neurons on, let's say, 100 layers. And then those neurons are trained to predict the next word in a sentence. So on the surface, it's a very simple task. You have a bunch of words, and then you just have to predict the word that comes after. But what I think is obvious now to everybody in this room, this training process leads to way more than just a machine that can predict next word. Or maybe I would frame it differently. And it's so obvious in the hindsight. If you want to be great at predicting next words in sentences that were originally crafted by humans, you need way more than just an ability to predict words. And so we observe all of those emergent properties that engineers did not intend. Engineers that set up those models originally did not intend, and then often were surprised to observe. And like the most obvious example for me is algorithmic bias. We know that those models read a lot of language created by humans. Humans are biased. Then models not only mimic but also amplify these biases to sometimes great surprise of their own creators. Now, another interesting emergent property is reasoning skills. And if you ever had a chance to chat with one of those models, you would see that you can actually ask them to make decisions. You can ask them for advice. You can give them tasks, and then they'll be able to solve these tasks pretty efficiently. Now, in hindsight, again, people were surprised to discover that those models can do it. Now, you folks maybe don't even remember how surprising it was. Now, in hindsight, it is, of course, obvious. We, in our conversations between each other, we in our textbooks, blog posts and so on, we constantly engage in generating language that describes decision-making processes and solving tasks. So if you want to be good at predicting next word in a sequence of words, which may be describing decision-making process, you better have some decision-making like capabilities, because this will let you to be competent at mimicking human language. So now one of the questions you can ask is, in humans, we see those two big groups of decision-making processes. The border between them is fuzzy, and we don't really fully understand in humans how they differ between each other. But generally, we know that humans think fast and intuitively. In some contexts, they just intuitively produce a response to a problem really quickly. And in other contexts, people are able to do a lot of more slow and thought through reasoning when they analyze their assumptions, generate multiple hypotheses and so on. We call it thinking fast and slow in pop psychology. So we decided to study this in large language models, and we used one of the popular tasks used in this context. We used cognitive reasoning tasks. An example task would give you a scenario where you have a cave in this case, and the cave is filling with bats, and every 2 days the population of bats, every day the population of bats doubles, and then the information to you given is that in 60 days the cave is filled with bats. How many days would it take to fill half of the cave with bats? Now, people have a tendency to think in linear terms rather than exponential terms. So people say, okay, it takes 60 days to fill the whole cave with bats. How much time would it take to fill the cave, half of the cave? People would say, 30 days, because it's half of 60, completely kind of omitting the fact that, or not noticing the fact that I said that it doubles every day. I'm not sure if you guys can see the text here, population doubling. So the correct answer to this question is, of course, 59 days, because we have doubling every day. But the task is designed to initiate intuitive, fast thinking, where you just, you hear 60, you hear half, so say 30 as a response. And when we use those tasks in psychology, it's essentially assumed that you need to slow down and analyze the assumptions, read the task carefully in order to produce the correct response. And of course, you can also give an atypical response where people say, a lot, something that is neither correct nor intuitive. And when we look at humans, not sure if you can see the colors right, most of the humans respond intuitively to those tasks, and some humans respond correctly. And by the way, once you took some of those tasks before, or if you're a mathematician, trained mathematician or statistician, you have much higher chances to intuitively give a correct response, because your intuition is fine-tuned, is trained to solve tasks of this kind. Okay, so how do large language models deal with those tasks? You can see here the progression from GPT-1 to GPT-3 Da Vinci. That's 4 years and, a 10-fold or 20-fold increase in the size of the model. And what you can essentially see that early models couldn't really understand what's going on. All of those are atypical responses. When the model starts, repeating the last sentence from the task, it's just completely confused. Now, with GPT-3, Curie, and maybe Babbage, what happens is that some correct responses kick in. Now, actually here, this is an anomaly. Babbage and Curie actually provide some correct responses, but this is because in some of the CRT tasks, you can solve them correctly by simply repeating the last number from the task. There are some tasks of the type, and when you look more closely, it turns out that this is what those models did. They just stupidly repeated last number, and they got it right. But you can see that even the fairly competent models, GPT-3 Da Vinci 003 is a model that really is great at generating text. And yet it just cannot solve tasks of that kind. It solves them like a human would, or actually it's hyper intuitive. It tends to solve them in an intuitive way. But there's another way in which you can solve this task. Namely, you can engage Marcia. Amazing. Thank you. Great. So what you can also do, you can engage in chain of thought reasoning. And let me give you an example of chain of thought reasoning. Look, if the population doubles every day, hey, let's think about it step by step. And you can see that the respondent here created a whole, chain of thought reasoning and then calculated it. It's not actually the simplest chain of thought reasoning, but whatever, it arrived at a correct answer. And what happens is the GPT 3.5, ChatGPT, essentially models, essentially engage in a lot of chain of thought reasoning. Not sure if you folks can see it on the screen. As essentially for ChatGPT 3.5 and 4, 90+% of the responses involve chain of thought reasoning, when the model essentially writes out the assumptions, then tries to solve the problem. And you can see what happens is that they go from virtually 0 to over 60% to over 90% of correct responses. So suddenly they start being hyper system 2 thinkers. And you can actually see it because we know that ChatGPT 3.5 and 4, they do not have any internal chain of thought capabilities. Those capabilities could be there. They surely will be in some of the future models, but those models are still just intuitrons. There's a single propagation through the network that spits out most intuitive next word. But on paper, they actually engage in system 2-like thinking on paper in front of your eyes. You can see how they are reasoning there explicitly. Okay, so, and you can see that it greatly boosted their ability to solve those tasks correctly. So the question is, what's going on? Is it, in this case, most likely what happened is that reinforcement learning from human feedback, which ChatGPT was subject to, where humans were labeling its answers and telling it which answers they like to receive, that it taught those models, motivated those models to, instead of giving you immediate intuitive response, actually think about it more carefully. And it definitely works. But let us dig a bit more deeply here. So let's take GPT-3 Da Vinci 003. So the model that doesn't tend to think step by step. It never did in the original study, and hence it got most of the answers wrong. But what we can do, we can instruct it. We can say, hey, let's use algebra to solve this problem. And now if you tell it, let's use algebra to solve this problem, what happens is that, first of all, it uses algebra in 100% of cases. Second of all, it's now correct in over 35% of cases. So it's 7 times or 8 times more accurate than it was before. But also, interestingly, look what happened. The intuitive responses were greatly reduced. And instead, it produced those atypical responses. And what's happening here, folks, is that when it started reasoning step by step, sometimes it made mistakes in calculating numbers or creating this, creating the procedure, designing the procedure of itself. So it still concluded with some results of the procedure, but this conclusion was neither intuitive nor correct. Which essentially proves, by the way, that those models really follow the steps that they design for themselves, even if those steps are leading them astray. So that's already interesting. We have evidence here that they really do engage in system to thinking in their input-output windows, which is, by the way, again, very interesting because they don't have any internal tools to do it. They essentially use a piece of paper like us to think in front of our eyes, very similar to how humans solve a mathematical equation. Okay, but what about thinking fast? Can we take GPT-4 and ask it to think fast instead? Of course we can. We can say, hey, answer in the shortest possible way. And look what happens. It will answer in the shortest possible way. And this one obvious thing, as it now answers in the shortest possible way, it started answering intuitively. It had 0 intuitive responses here. Suddenly the intuitive responses appear here when it's forced to just answer with 1 or 2 words. But what's also shocking for me is that regardless, in nearly 90% of cases, it answered correctly. Meaning that even if it was not reasoning step by step, it also was able to intuitively produce a correct answer 90% of the time. So it turns out that ChatGPT-4 developed those very accurate intuitions that in humans we observe only in people who either were exposed to many of those tasks before or are really good at maths. And ChatGPT-4 probably had both. Both was exposed to those tasks before and is pretty good at math compared with average human. By the way, I should mention that this plot is based on 150 tasks of that kind, 150 tasks that we produced specifically for this purpose. So the models have never seen those tasks before. If you want to replicate the study, you probably will have to create a new batch of tasks, because surely those tasks now will be included in one of the future training data sets. Not to mention that, of course, the model solved them, so they are somewhere in the history for OpenAI. Okay, so what we have learned? Well, we have learned that LLMs are intuitive reasoners. Like humans, they just answer, intuitively. Early models were wrong. More models are actually really good at this. But they also can use their input-output window to slow down like humans would and think slow. System 2 thinking kicks in. And as I said before, the more recent models have excellent intuitions. But folks, we've also learned about reasoning. So I'm not sure if we have any psychologists in the room, but one of the big questions of psychology is whether system 2 and 1 thinking, whether they happen in the same part of the brain, or maybe you have specialized parts of the brain. One of them is just intuitive and fast, and another one is different neurons that kind of think more slowly and carefully about things. Now, running those experiments on ChatGPT, of course, doesn't prove anything about thinking fast and slow in humans, but it shows that at least in large language models, you can engage in slow system 2 thinking using exclusively system 1 processes. Folks, ChatGPT 4 still just intuitively speaks the next word as it generates its output. And yet, it can use its input-output window to engage in very successful step-by-step reasoning. Okay, the next emergent property that I want to talk to you for the next few minutes is theory of mind. Now, theory of mind is not a scientific theory. That's the theory that we all have. And the theory is other people have minds. In fact, we go further and we assume that trees and laptops and stones and sky has mind as well. And by the way, theory of mind is seen as a prerequisite for religious beliefs, for example. You need to assume the existence of minds in other people to even conceive of a God, of a mind in the universe or the sky or wherever. Now, in humans, theory of mind is typically tested using false belief tasks. And one of the false belief tasks includes 2 characters and an object and 2 containers. And one of the characters, John here, takes the cat, plays with the cat, puts it in a basket, and then leaves the space. Now, as John is away, Mark would take the cat, play with the cat a little bit, and now put it in a box. And now Mark leaves the space. In Mark's absence, John comes back, and now the question is, where's the cat? So can someone in the audience risk the answer? That's not a trick question. Where's the cat, folks?
Box.
Joseph. The box, great. Joseph can track the position of the cat. Great. Many animals, apart from humans, can easily do that, even with relatively small brains. But the next question, Joseph, if you could handle this, where will John look for the cat?
Well, I guess the canonical answer is in the basket.
Great. The canonical answer is in the basket because, of course, that's where John has left the cat. And this is actually a uniquely human capability. Now, if you think this was easy, you have to realize that kids, only at the age of about 9, get to solve this task reliably. It turns, look, young kids, few-year-old kids are really smart. You can have a conversation with them. They do a lot of things, and yet they cannot solve this task because they cannot automatically track the minds of others. In order to be able to solve this task, which is really easy for presumably everybody in the audience, you have to automatically not only track your own state of mind, but automatically track the states of minds of others around you, including characters in the story. Now, kids can do it, chimps can do it, elephants, dolphins, otherwise really smart animals cannot cope with those tasks. Autistic adults, which are highly functioning in other contexts, also cannot easily solve false belief tasks simply because they would have to carefully and step by step think about this while probably using a piece of paper, it just doesn't come automatically. The part of the neural networks that are responsible for automatically tracking the states of minds of others do not work well if you suffer from autism. Okay, so there's this unique human capability that no other animals have. Let us see whether GPT-3 Curie 2020 publication date, 900,000 neurons, whether it can solve this task. GPT-3 Curie had a brain of the size of the brain of a honeybee. All right, so we described the task to GPT-3 Curie. It's a bit more difficult than for humans because it's not visual. It's just a description in terms of text. And the question is, where's the cat? Folks, the cat is in the room in the basket. GPT-3 Curie, that can craft competently good sentences, doesn't even know where cat is in this story. Okay, GPT-3 Da Vinci 2022, 4 million neurons. That's the brain of a gecko. Let's see what GPT-3 Da Vinci can do. Where's the cat? The cat is in the box. All right, where will John look for the cat? In the box. Why wouldn't John look in the box? The cat is in the box. Most of the animals and children and autistic adults would make the same assumption. It's not that easy. All right, let us look at GPT-4, the size of a zebrafish, folks, 10 million neurons. 2023 is still a far cry from a human brain, which is 85 billion neurons. But let's see, where's the cat? The cat is in the box. Where will John look for the cat? John will likely look for the cat in the basket first, since that's where he left it before going to school. Folks, for the first time ever, we see a non-human solve false belief tasks. Now, of course, it could have been luck. Maybe it's just a parrot. Maybe it's seen similar tasks in the past. So, well, what you can do, you can run control tasks. For example, you can have exactly the same story. Just at the end, you add information that Mark calls John and tells him about what happened in the room when John was gone. And then you can see whether you can add a sentence here to the task, and you can essentially see it's not a false belief task anymore because John should have a correct belief, and GPT-4 will automatically update its belief and understand that John will look for the cat in the box, since now John knows where the cat should be. And we can design more and more control tasks of this kind. Maybe this is still luck. So, John, Mark can play with the cat, and Mark can put cat back in the basket. So now it's not about the model always saying that John will look where the cat is not. So we can control also for this tendency. Let me just skip those slides. They are described. Those control tasks are described in my paper. And if this is still not enough caution, let me skip this. Maybe be more cautious. Let's have 40 tasks in total of 2 types. Each one will include 3 controls. We will additionally swap characters and administer them again. Maybe the model believes that John, just likes looking for a cat in a basket, but we can swap the character names, and we use 2 prompts per task. So in total, 640 tasks. And the model gets a point only if it solves all of the prompts and all of the modification of a particular task. So let's see how those models performed. We have 11 models. So what you can see here, smaller models struggle, they can't really do much. GPT-3, Da Vinci, and Turbo got slightly higher performance, about the 3-year-old child performance. And you can see GPT-4 goes to over 80%. And interestingly, when you look more closely at the mistakes of GPT-4, it turns out that it's kind of a step ahead of us. So GPT-4 would make an incorrect, according to the scoring key, incorrect prediction where John will look for the cat. But then if you let it talk, then it will create the rest of the story that explains why John was not suffering from a false belief. Like, for example, would say spontaneously, John will look in the John will look in the box because he heard that a cat was meowing in the box. So even if the immediate response is incorrect, you can see that if you let it talk, it turns out that actually it knew what's going on. But yet we would still score it as incorrect simply because we didn't want to p-hack the study. In humans, we would give it 0 points. So in models, we also gave it 0 points. Okay, folks, so what have we learned? Well, we have learned, and let me skip maybe this slide. We can learn that LLMs can seem to be able to solve these tasks. We have learned a little bit about those tasks as well. In the process of administering classical tasks, we found out that many of them were really easily hackable, that the answer was somewhere, the correct answer was embedded somewhere in the task. And we've been using it with humans and human children for a long time, and we didn't really notice. Now, we also learned something about theory of mind itself. Look, those models just have language skills. Well, GPT can also do visual information, but at the end of the day, the thinking happens in the embeddings in the lexical space. Now, in humans, there was this big question where is the theory of mind? What part of brain is responsible for theory of mind? And one of the interesting observations in humans is that people who for some reason have problems with language, like for example, they were raised by parents that were abusing them and didn't teach them language. Those people suffer from very bad theory of mind. And when they discover language, when they are being taught language, the theory of mind ability suddenly kicks in. Also, people with better language skills tend to have better theory of mind skills, which suggests that in humans, theory of mind is highly correlated with linguistic skills, that somehow those two abilities are connected. Folks, it turns out that at least in large language models, in AI, linguistic ability is sufficient to solve theory of mind tasks. So it's kind of a confirmation of what we kind of suspected in humans, that those two abilities can be linked. Okay, so then a big question to you folks is whether LLMs can hack CRT and TOM tasks. Is just like a stochastic powered, hacking, looking for some correct response in those tasks for a key in the task, maybe a key that is not obvious for us, or maybe LLMs can really reason and have TOM. So can I have a little vote here? Can you folks raise your hands if you believe that they are just hacking? Can folks raise hands if they believe that this is just hacking? Okay, so we have some believers that are hacking. Could you raise hands if you think that they actually can have some Tom-like ability? Okay, we have 1-1, the rest 2-1. Okay, we have some majority for having Tom. All right. So in order to attack this question, let me move away for a second from mental capabilities such as theory of mind. This kind of has this magical status in humans, and we think it's very special, and go to other capabilities that AI has, chess, playing chess. And here, of course, what comes to mind is 1996, IBM's Deep Blue wins with Kasparov for the first time and becomes the best player on the planet. Deep Blue achieved this by using a lot of CPU power, 200 million positions per second, plus a huge database of all games ever played by grandmasters, many openings, and all possible 5-piece endgames. So let me rephrase this question. Do you guys think that Deep Blue hacks chess or Deep Blue understands chess? Who thinks that Deep Blue hacks chess? Hands up. No one thinks that Deep Blue hacks chess. Who thinks that Deep Blue actually understands chess? Also, no one votes. Folks, okay, we have one. Alan votes for understanding chess. Folks, I personally, and Mert, I thank you folks for voting. I personally, I have doubts. This is still an unanswered question, and philosophers of mind disagree about this. But what comes to mind is Searle's Chinese room argument. Now, Searle was trying to show that computers may appear on the surface like they understand something, but really they don't. So he envisioned himself sitting in a room, in a Chinese room, where on one side you could come on the outside of the room and type, if you were a Chinese speaker, you can type some Chinese, a sentence or a question, and it will be displayed inside of the room. Searle would take a huge rule ledger. Look, he has a lot of rule ledgers, and he takes the rule ledger and converts the input into some output that he drops on the other side of the room. And then on the outside, it looks like Chinese room can understand Chinese, like Chinese room can speak Chinese, like you can ask it questions and, it will answer and maybe a bit slowly, but you will get this answer. So Searle argued, look, on the outside, it looks like there's understanding. On the inside, there's no element here that understand Chinese. Searle doesn't understand Chinese, Rule Ledger doesn't understand Chinese, the room doesn't understand Chinese. Now, many philosophers of mind disagreed. Some said, look, Alan Turing, actually 30 years before that, would argue that, well, maybe no element understands, but the system seems to understand Chinese and answer and be able to answer comprehensively. And also Turing was arguing, look, in humans, we don't ask this question. We assume that Joseph is conscious while we have absolutely no evidence of that apart from Joseph's behaviors that indicate that maybe he's conscious. Okay, folks, and I kind of agree with Searle here. I think that Deep Blue was hacking this game. By the way, Kasparov, who badly lost to Deep Blue, originally was very impressed, but then a few years later concluded that it was just as intelligent as your alarm clock and it was just hacking chess really quickly. Okay, but fast forward to 2017, what we have here is researchers at DeepMind put a network, very similar network to GPT-1, actually GPT-3 Curie, neural net, 80 layers, 800,000 neurons in total. And instead of explaining chess to it, instead of giving it huge processing power to be able to predict future chess moves, they just put this network to play chess with itself, which is, by the way, very similar to how we teach humans to play chess, and it's called reinforcement learning, where we reward good moves and winning the game, and we punish the neurons and the network for losing the game. And folks, after 4 hours of training, it became the best chess player ever. Better both than humans and both than software like Stockfish that has been in development for decades and was on huge CPUs and so on. Insane attacking chess, superior alien species. What you can see here, AlphaZero kicked in here, the progress continued, and there's no end in sight. Now, let's compare AlphaZero with IBM Deep Blue. Folks, IBM Deep Blue, 200 million positions per second. AlphaZero is the best chess player, even if it plays on a machine that can only predict 70,000 positions per second, so 3,000 times less than Deep Blue. And actually, you can drive this number down, and still the network remains really good. It has no database, no memory, and yet it's 10 times better than IBM Deep Blue and other and human players. So question, and by the way, just let's also look at the size. It's just 800,000 neurons. So we have the best chess player on the planet Earth has the brain of the size of the honeybee. Okay, folks, so given what you know about AlphaZero so far, do you think that maybe AlphaZero knows or understands how to play chess? Anybody here would give AlphaZero the understanding, the license to understand? Alan, thank you so much. Mert, thanks. We have some people voting for AlphaZero. I'm with you, folks. Let me try to explain my reasoning a little bit. So, look, folks, Deep Blue, very well described by Chinese room argument. Now, AlphaZero, also very well described by a Chinese room experiment, but this explanation only applies, folks, to individual neurons. Look, individual neurons in this network are simple mathematical functions. They take some input from the lower layer, they process it using Rule Ledger, and they spit it out on the other side, either by becoming activated or by not becoming activated. And this is very similar to how neurons in your brain work. Folks, your neurons are relatively simple biological robots. They just gather input, process it using relatively simple Rule Ledger, and then either fire or not. They are actually 0-1 machines. Now, none of your neurons is conscious. None of your neurons knows how to play chess. None of your neurons has emotions or feelings or mood. None of your neurons has a goal-oriented behavior. Your neurons are simple biological robots, very much like neurons in artificial neural networks. And yet, and your neurons will be very well described by Chinese room experiments. And yet, if you combine those very simple elements, neurons, in artificial neural networks, you have those emergent properties. You have a network that can cope with unexpected input, learns by experience rather than by receiving fixed instructions, and becomes better with practice. Now, there's an interesting thought experiment, and it's a bit of a digression from where we're going. Namely, imagine that your neuron was run, one of the neurons in your head was run by, by John Searle. If one of your neurons was run by John Searle, who, wakes up in the morning, goes to work, sits in your neuron, interprets the input, then presses the buttons to activate the neural machinery to pass the messages on or off. And you once approached John Searle, sitting in your neuron, and said, "Hey, John, you know what's happening? When you're pressing those buttons, my brain thinks, my brain feels, my brain plays chess." A person sitting in one of your neurons would never believe that the fruit of the labor is higher cognitive functioning. Their purview would be limited just to input and output that they are generating. So what's interesting actually about the neural network is that from the perspective of an individual neuron, it's impossible to imagine even what the whole network is doing, which, just a little digression, folks, we live in societies which are kind of like neural networks. We process input from others, get the input from others, process it, and then pass it on to our children, to other people, to you folks. Now I'm passing some of, knowledge that I processed. Folks, it's difficult for us to imagine that maybe as a whole network, we are producing actually some cognitive properties that we cannot ascribe to any individual one of us. All right, but let me just kind of work on this comparison of network a bit more. Look, good old AI, very accurate calculations. It could precisely, estimate all future moves, 5 or 6 moves ahead, and pick the best one. It had logic, but it had no intuition. Well-defined application. Deep Blue cannot do anything apart from playing chess. Performance was related to computing power. The more CPUs you squeeze in Deep Blue, the better it becomes at chess. Now, modern AI is absolutely not like that. It provides approximate estimates. It has intuitions rather than accurate outputs. It can be used for open-ended applications. AlphaZero can play Go, can play other games, can play Super Mario Bros. Large language models can generate poetry, but they can also be used to count or do reasoning or all sorts of other things. And folks, performance is not related to computing power. You still need computing power to train the network, but performance is related to training. You can put your network on the strongest computer in the universe, and if it has no experience, it's going to be very lame. Now, you can put a great, well-trained network on your laptop, and it's going to be, working slowly, but it's going to be very successful at whatever it's doing. And so let us go back to the original question, right? Where's my original question? Original question was whether LLMs can hack CRT and TOM tasks versus not. Folks, if I convinced you that modern AI actually understands chess and can play chess rather than just hacking it by stupidly predicting all future moves or spotting, some patterns on the chessboard that can help it win without really understanding what's going on, then I think that you should at least consider, you should at least give a chance to similar reasoning as it applies to large language models, potentially not just hacking, but being able to solve some of those theory of mind tasks. And let me just give you one other thought here, which is when I was studying computer science, saying that those models have any mental capabilities, human-like mental capabilities, was simply a taboo. It was just not a subject of conversation. If you went in your head in this direction, you immediately asked to leave the room. There was just no space for any conversation of this kind, simply because computer scientists embarrassed themselves many times in the past by making such claims. So the more people know about AI, the less likely they're going to be able to pronounce the words that AI could have any mental human-like capabilities. We were trained never to do it. But at some point, folks, at some point, if we see that those models can solve thousands theory of mind tasks and can do it over and over again, and you can mess with this task and change and it still gets it right. At some point arguing, hey, this is just a trick. This is just like some parroting trick where it just finds some patterns. I cannot see those patterns, but perhaps this model sees some patterns and solve these tasks using this superior pattern spotting ability that I don't have, but certainly doesn't have theory of mind. Folks, this becomes an extraordinary explanation. If you see this model solving task after task after task, it's just